Today, we have with us Professor Krishna Podel, who is an assistant professor of forest biometrics at the Mississippi State University. He received his bachelor's program in forestry from Tribhuvan University, Nepal, MS degree in forest biometrics from Louisiana State University, and MS in statistics and PhD in forest biometrics from the popular Oregon State University. His primary research interests are related to the integration of statistical methods and multi-source data set to better understand the forest management problems to make well-informed decisions. Before joining Mississippi State University, he worked as a postdoctoral research scholar in forest management and biometrics at Biometrics Lab at Oregon State University, focusing on refining volume and biomass model currently used in the official U.S. greenhouse gas inventories. He has collaborated with faculty from different U.S. universities and researchers at the United States Forest Service in different research projects. Internationally, he has collaborated with researchers from Nepal, Vietnam, and Turkey in several forest measurements and biometric research projects. And I believe in the next version of this profile, he is also going to add he has collaborated with the Achievers Gathering, one of the popular organizations in Africa, poised at impacting the lives of young people. So without wasting much of our time, I would love to welcome Professor Krishna Podel for his presentation. Thank you.
All right, thank you, Joshua, for that great introduction, and thanks for the invitation to talk about above-ground biomass estimation with R today. Hopefully, something that we will discuss today will be useful for many of us. Let me share my screen if I can. And okay, can you see my screen?
Yes.
Okay, good. All right, I guess I can minimize that. And let's make it full screen. All right, thanks again, Joshua, and everyone for joining today. My name is Krishna Podel, and I'm an assistant professor of forest biometrics here at Mississippi State University. Today we'll talk about above ground biomass estimation with R. So this is the outline. I'll provide a brief introduction about myself and my research, and then we'll talk about forest biometrics in sustainable forest management, how biometrics can help us in sustainable forest management. Then we'll talk about what are the common approaches that we use in biomass estimation. Then briefly about, I think I have a couple slides about introduction to R and its application in forest biometrics research. And then later I will do some hands-on example for estimating biomass using R. I did post the link to data and R code on chat, but I think that got lost because we had to restart the meeting. So I'll post that again later when we get to that point. Okay, so brief introduction, like Joshua mentioned, I'm an assistant professor of forest biometrics. I started this position in 2018. Before doing that, before coming here, I was a postdoc scholar at Oregon State University, and I got my PhD in forest biometrics and master's in statistics from Oregon State University, my master's in forest biometrics from Louisiana State University, and my bachelor's in forestry from Tribhuvan University, Nepal, where I am originally from. And my primary research focuses on sampling and modeling. Recently, or in the last few years, I've been focusing on sampling and modeling for biomass and carbon estimation. I have also worked with the growth and yield models and currently working on some short rotation bioenergy crops and developing growth and yield models for them. I also work with forest inventory data and fusing or combining that with the remote sensing data. For example, small area estimation. So basically, fusing multi-source data for our forest inventory problem. And in terms of teaching, I teach mainly 3 courses: forest biometrics, which is taught for both graduate and undergraduate students in our department; environmental measurement, which is sampling design, which focuses on sampling design, and that's designed for our natural resource environment conservation program students, and advanced forest inventory, which is a graduate level course in forest inventory. We talk about regression analysis, growth and yield models, application of different regression models, starting with a simple basic linear regression model to more complex models. So that is my background information. Now let's talk about what forest biometrics is and how it is useful for sustainable forest management. I think you guys had some speakers before saying hi. I think he talked about what is forest biometrics as well. And I don't think there is a one standard definition for forest biometrics, but it is a science of forest measurement. So what it does is it deals with the application of mathematical statistics so that we can use it to analyze the characteristics or features of trees and stand. And Arnie 2006 from Forest Biometrics Research Institute, he provided more comprehensive definition for forest biometrics, which is it encompasses the quantification of biological and physical characteristics of trees and associated vegetation, insect, disease, wildlife topography, so many things. So we are focused on trees, but how they are associated with other aspects of the environment. So biometrics it has two components, biological and measurement. So it's a biological measurement, but we are focused on biometric forest measurement of forest. So how can biometrics help in sustainable forest management? So if we want to manage our resources sustainably, then we need to know, or we need to have the up-to-date information or up-to-date inventory of our resources. However, because the forest resources are spread across the large area, so we cannot measure all the items in our target population. That's one of the main challenges we have. And through biometrics, we can learn about different sampling designs, which help us in getting the unbiased estimate of our variable of interest. For example, are we interested in volume per hectare or per acre? Or are we interested in carbon sequestered by a forest? So those kind of things we can use sampling designs. I think Dr. Matt Russell talked about sampling designs applicable in natural resource management. So for those of you who joined the previous seminar. And the second problem in resource inventory is we cannot, even when we sample, then we cannot measure some of the variable of our interest. If we take simple example of height and diameter measurement for trees, diameter, it's easy to measure, but height, it is difficult to measure. So in that case, what we can do is measure diameter and height for sample trees and then develop regression models, which we learn in biometrics as well. And the third problem is we are not just interested in what is out there right now, but we also want to know what the forest or the resource condition will be in the future. So for that reason, we need growth and yield models, which are also tools developed using biometrics research. So basically, three main problems in managing our resources sustainably, because we want to get the up-to-date information, but cannot measure all items, cannot easily measure some, and we need to know what the standard, what the forest will look like in the future. And biometrics, knowledge of forest biometrics can help us solve those problems. And then, so to summarize, so how does forest biometrics solve that problem? It provides information at different spatial scale, so that we can calculate what is the allowable cut, how much volume we can get out of the stand on a sustainable basis. And that helps us in developing sound forest management plan. And we can also use that information for evaluating different management options. And what are some silvicultural treatments we need to apply to meet our target objective. For example, do we need to do some kind of thinning? is the stand ready for harvest? Those kind of things. We need some quantitative measure, and Forest Biometrics helps us in that. And it also helps us in avoiding conflicting land uses, addressing emerging issues. For example, carbon sequestration. That issue is also, or we need Forest Biometrics to be able to quantify forest carbon sequestration as well. So basically, our objective usually in forest measurement is we want to know the mean or total of the variable of interest, for example, volume per acre per hectare, or carbon per hectare. But because the forests are distributed over large area, so we cannot actually measure all the trees. So that means we use sampling and statistical models through Forest Biometrics, and then use sample-based estimate as the guiding attributes for decision making. So these are some of the examples of Forest Biometrics application that I have used in my research. First, the natural resource sampling. For example, what is the appropriate or what is the best method to sample for estimating forest carbon? And growth and yield models, what the stand will look like. I have looked at multiple or different types of growth and yield models. For example, whole stand model, stand table projection, diameter distribution models, if you guys are familiar with those. And also allometric model development for biomass and carbon estimation. This is critical, and that's the main focus of today's talk. And modeling tree taper and volume. So for example, depending on what is the merchandising diameter limit, we need to know what is the upper estimate diameter. So for that, we need tree taper and volume equations. And biometrics is one application of Forest Biometrics research is in that area. Similarly, remote sensing technique, we use different type of remote sensing data for answering our problem or natural resource management questions. And also incorporating climate variables in our growth and yield models, because of the changing climate, we can expect different growth pattern in our forest. So we need to incorporate that, and biometrics is one application, or we see one application of biometrics in that area. And short rotation woody crops, these are the dedicated bioenergy crops that are planted for producing biofuel. And if we want to identify how much feedstock this plantation can supply, then we need to understand the growth and yield of these type of crops as well. And also very popular these days, machine learning in forestry, different types of artificial neural network and different methods. Those are used in forest as biometrics tool in different forestry applications. So these are basically some of the research projects that I have worked on, and these are related to the Forest Biometrics. Okay, so now let's move forward with the approaches to estimate biomass, and we'll focus on above ground biomass today. So first, let's define the biomass. So it is above and below ground, living and dead mass of the trees, shrubs, vines, and root. And we usually express this as open dry weight. And why do we care about forest biomass? Because it is the critical variable in determining what is or how much carbon is our forest capturing. So for that reason, we have to estimate biomass. And we can divide this biomass into or forest biomass or tree biomass into two different components, above ground biomass and below ground biomass component. Above ground, for the tree, it would include stem wood biomass, stem bark, branch and foliage or leaf. And for the below ground component, we have fine and coarse roots. And why do we care about the components is because they have different values. For example, stem wood for biomass is used for information about the stem wood biomass is used for timber sales. Crown biomass, including foliage and branch, it provides information for fuel load assessment. It can be used to develop our fire management strategies. Depending on how much biomass is left over after harvesting, we can decide how much fuel is in there, or we can determine that, and that can be input in our wildfire models. And also, if we want to use these leftover material for bioenergy production, then we need to know what is or how much is the carbon or biomass in ground component. So that's why instead of just, in addition to the total above ground and below ground biomass, we are also interested in different component biomass. And estimating biomass, it's not new. The interest started or began in early 1960s. And these days, because of different climate change agreements and action plan, we have to estimate carbon. And instead of estimating carbon directly, we estimate biomass and then convert that into carbon estimate. And for example, RED Plus, they have the provision for carbon credit by depending on how much carbon your forests are sequestering, then you get credit for that. So for that reason, also we need to, or there has been an increase in interest in estimating biomass. Also, if we want to reduce fossil fuel emission by using biomass as the renewable source of energy, then we need to know how much biomass is available for biofuel production. And that information is also useful for establishing where we should locate our bioenergy plants. So for that reason, also we need biomass estimate. And so there is two parts. One is biomass estimation, and the other is biomass measurement. So biomass measurement would be actual measurement. Estimation would be based on some models or sampling. So most biomass studies, they use open dry biomass or open dry weight and calculate the biomass of different components separately. And this is for measurement. If we have young trees, then it is measured usually by fitting the sample tree and weighing the entire tree. So this is for measurement. And but it is prohibitively expensive. It is difficult for mature trees because they are large. So it takes it will be labor intensive and it will be costly as well. So instead of measuring the entire tree, we use some kind of sampling. And root biomass. Before starting this talk, I talked with Joshua about the below ground biomass as well. And there is comparatively, there has been fewer research focused on below ground biomass because it is difficult and also costly. So that's why it's been, I don't know, ignored is the right word, but it has not been done as much. And so how do we measure biomass? So let's first focus on how do we measure biomass, because when we want to estimate, then we need the some measured values or Y values for our regression model. And how do we get that? So the first step is to collect data. So that, let's say, if we want to measure the stem wood biomass, then how do we do that for mature trees is determine stem volume by sampling or destructively sampling some trees. And we measure, once we harvest the tree, then we measure diameter. We section those logs and then measure the diameter at both ends. And we can use volume calculation formulas, for example, Ismailian's formula, and obtain the volume of each section. Then we also get some sample disk of predetermined thickness. It can be at the midpoint of the section or from both ends of the section. And then once we get that, then we use the ratio of disk weight to disk volume, like here, and then multiply that by the section volume, which we calculate using Ismailian's formula. So that would give us the section weight. And once we get the section weight for all the sections, then we can add them together to get the total stem wood biomass or green weight. And then we also get the subsample from disk so that we can get the ratio of green to dry weight, which we can apply to convert that section green weight into section dry weight or total green weight to total steam wood dry weight. And for the branch, it is more challenging because there are too many branches. The idea is first we measure diameter at the base of all branches, then take a random sample of branches and obtain their individual green weight or dry weight. And then these observed branch weights, individual branch weights, they are regressed, or we fit regression model that predicts the individual branch weight based on branch diameter or branch basal area. And then once we calculate the individual, once we have the model for predicting individual branch weight, then we can use the diameter measured, step 1, diameter of all the branches, and apply that regression model to get the green weight or dry weight of all the branches. And once we have the estimated dry or green weight of all the branches, we add them together to get the total tree level branch biomass. And then at the end, we relate that tree level branch biomass, not the individual branch level, but individual tree level, with the diameter at breast height and other variables. For example, total tree height. Sometimes we use height to the base of live ground, so that we can predict the total branch biomass for the individual tree instead of just the individual branch. Then for the foliage or the leaf, we use the same branches that we measure for branch wood biomass. And for example, we can select a 25% random sample of branches and get the foliage green weight for each branch separately. And then fit same as in branch wood biomass, we fit regression model to estimate foliage biomass from branch diameter, and then subsample for converting green foliage into open dry weight. And then once we do that, then at the end, we add the individual tree foliage biomass to get the total tree foliage biomass, and regress that with the tree diameter, height to the crown base, or total tree height. And the other components include bark and root biomass. Bark, we do the same as in steam wood biomass, but instead of using diameter inside bark, now we use the diameter outside bark. Then we can calculate the difference between inside bark biomass and outside bark biomass and get the bark biomass. For the root, it is difficult. We need to excavate the entire root system, which is virtually impossible. So subsampling is necessary. And there is not enough, there is not large data set for the root biomass. And so this is, or so far what we talked about is biomass measurement. Okay. Of course, we had regression model for individual branch biomass and foliage biomass, but this is also, that is also part of the measurement. Then the next is how do we estimate? So once we have the data for developing model, so how we estimate the biomass. So before starting that, let's talk about the biomass estimation approach used in the official greenhouse gas inventory by the United States. In the US, there is a forest inventory and analysis program, which is part of the US, or which is a program under US Department of Agriculture Forest Service. And it is called the Census of the Forest, US Forest, because they have permanent plots, and those are repeatedly measured. And that inventory data is used as the guideline, or used as the main starting point for estimating forest carbon. So tree measurement, once we have the tree measurement, then we need biomass estimate for those trees. So in step 1, or in this case, we have tree level information, for example, diameter, height, and other variables, tree level variables. And then once we have that information, we have different type of biomass equations that we can apply to those inventory data. until 2009, the US used to use DBH-based or diameter-based equations fit by species group, and those were developed by Jenkins and others in 2003 and 4. And since 2009, the US is using a method called component ratio method. So basically, the idea in component ratio method is first use volume equation to get the gross volume, which is without accounting for defects, and then subtract that defect to get the sound volume, and then convert that sound volume using wood density to get the bole biomass, and then using some equations from Jenkins, then calculate some kind of adjustment factor, and then calculate other component biomass. So it's a kind of convoluted process, but it starts with the volume data because there is a really large data set for tree volume, and because historically volume estimation has been the focus, but biomass has not been historically. It has not been studied as much as volume. So that's why to utilize that large volume data set, the estimation of biomass starts with the volume estimates. And so what are some of the limitations of those methods? For example, here, the DBH-based equations, if we, for example, using this example with 90 trees, I calculated for Douglas fir, one of the major species in Pacific Northwest in the US. If you added height instead of just DBH in the model, then you could reduce root mean square error by 9%. They provided, the existing method provided the comparable results for smaller trees, but for larger trees, the error was higher. So what we did is in 2012, there was a nationally scaled effort to estimate biomass for the entire United States. There were 7 different universities involved, and it was led by the US Forest Service FIU program and Mississippi State University. So I was at Oregon State University, so I started working on that. And then when I came to Mississippi State University, I continued that collaboration, and other universities were also involved. And what we did is we developed a consistent sampling protocol for the national sampling effort, and also compiled legacy data from past studies. So with that data, new and existing previously published data, we evaluated different sampling designs, developed new methods, and to estimate the total and component of above ground biomass. Still, we did not do below ground biomass, but this was for the above ground biomass. And we also looked at different approaches to deal with missing component. For example, in historical data, there were some studies where people looked at total biomass and just the stemwood biomass. They left the bark biomass. So how to account for the missing component, missing bark component. So different approaches were tested, some imputation methods, did that. And the result of this is there will be new equations and methods that we will be using in the US for official greenhouse gas inventory reporting to the UN starting hopefully end of this year. So far what I talked about is measurement of biomass and partly the estimation. But now let's focus on biomass estimation. So let's say that we have the data where we have, let's say we did some destructive sampling and we obtained the data for total above ground biomass and different components. And now, because biomass measurement is destructive, so if we want to estimate, or if we want to know how much biomass is in the forest, if we wanted to measure, then we would need to harvest all the trees. But we don't want to do that, right? So that's why we need to look at the methods that can help us in getting or estimating the biomass without having to destructively sample trees. So there are 2 common approaches. The first approach is estimate the components and add them together to get the total. common methods we use for that is we can use linear least square regression or ordinary least square regression. It can be linear or non-linear. And also we can fit model as a system of equation using seemingly unrelated regression. That's a very common practice. And the second approach is first estimate the total and then distribute that into different components. In this case, we use some kind of generalized linear models. And so ordinary least square, which is, for example, simple linear regression, we can use ordinary least square estimation technique. And when we have multiple equations, then we have to, because we will be using the same data set for fitting multiple equation, that means we need to take into account the error structure. So using the seemingly unrelated regression, it allows the inclusion of dependencies among the error, because we have component equation and then the errors, they can be correlated. So we can use seemingly unrelated regression to address that. And they can be, or commonly there have been some single entry or DBH only and extended, meaning multiple entry, DBH and height or crown length and other predictor variables. And there are different model forms people have tried, but most common is in linear. Usually it is the biomass models are fitted in log scale. And so ln y, so that's the natural log of component biomass. In x1 and x2, we have independent variables. X1 usually deviates, and x2 can be any other potential predictor variable for biomass. And we can also fit this equation as a nonlinear equation like this. If we take log on both sides of this equation, then it would become linear. And there is also another power model people use. So many different type of equation form used, but these models act better when we fit that as a linear model in log scale. And for the generalized model, so this one would be aggregation approach. And for the disaggregation approach, we can fit a simple linear model, not simple linear, but simple or just a linear model to get the above ground biomass, total above ground biomass. And then we can use different generalized models to predict component proportions. For example, beta regression is one, Dirichlet regression is another one. And there are other options as well, but I talked about this because these are the models that I have used. So basically get the total and then get the proportion, what percent should be in each component. Looks like there's some chat. Okay. So, and the differences between beta and Dirichlet regression is beta, we fit equations independently. So for example, if we have 4 components, those components will be independent of each other. But Dirichlet, it fits the equations simultaneously so that it behaves well, or it behaves better than beta regression. And so why do we care about these instead of using ordinary least square? Why do we care about these different type of regression models, generalized linear models? Because if we want to predict the proportion, then they have different properties. For example, they are bounded between 0 and 1. When we fit actual biomass, for example, in terms of kilograms, then the values would be between 0 and however many kilograms the biomass is. But if we want to predict the percentage of biomass in each component, then they would be bounded between 0 and 1. 0% and 100%. 100% would be 1. And for that, the effect of explanatory variables, for example, DBH height, that can be nonlinear. And the variance decreases when mean gets closer to one of the boundaries. So when mean is close to 0 or 1, then the variance decreases. So that means we need regression models that have capabilities to address those challenges. And beta and Dirichlet regression, they have that capacity. So that's why we can use them for predicting proportions. And briefly about the beta regression, it was introduced by Ferrari and Criveri-Neto in 2004. I'm not sure how much experience everyone has in fitting generalized linear models, but in generalized linear models, we have a link function, and then we have the metrics of dependent variable and the regression coefficients, and this is related to mean through that link function. So like I said, this G is the link function, and in beta regression, we can use different kind of link function. And what is the effect of that is what kind of link function we use determines how the prediction will be made. So for example, if we are using logit link function, then mean or estimated mean will be calculated this way. And Dirichlet regression is based on the Dirichlet distribution, which is the multivariate. In beta regression, we have one component, but in Dirichlet regression or Dirichlet distribution, we have multiple components. So it's a multivariate generalization of the beta regression or beta distribution, and it is useful for compositional data. Compositional data is if we have different parts and then they add to one, then we have a compositional data. For example, biomass proportion, we have, let's say we have 4 components: stem wood, stem bark, foliage, and branches. And then if we use the proportion or percentage, then they add to 1. So in that case, the Dirichlet regression is useful. And one advantage or one better property of the Dirichlet regression is when we fit different components simultaneously, when we model them simultaneously, meaning together, then the sum of the predicted values for different proportion will be 1. And also, same as in beta regression, we can use different type of link function, and that determines how we calculate the predicted value. And if, for example, if we are using log link function, then we would calculate by just exponentiating the eta. It's called eta. So that's the linear predictor. So basically, once we measure the biomass, then we fit regression models. There are different types of regression models available. And once we fit the model, we need to evaluate how good they are. And common evaluation statistics, we use coefficient of determination, R squared, which tells us how much of the variation in dependent variable is explained by the independent variables. Bias, or the mean difference in observed value and the predicted value, and also percentage. And root mean square error, which combines both bias and the variance, and also the percentage of root mean square error. And then we look at the mean absolute percent error, MAP. So mean absolute percent error. And that's also another commonly used statistic in evaluating the model fit. And then model validation is, I would say it's not that common because the biomass data is usually not that large. So, but if it is done, usually it is done by data splitting, sometimes using leave one out. So for example, you leave one tree outside of the data and then fit model using the remaining trees, and then apply the fitted model to that one tree, and then calculate the evaluation statistic like bias, R square, and so on. And in data splitting, for example, we can divide data into 70% for model fitting data and validation data set for 30%, using 30% for model validation. So basically, we use feeding data to get the coefficient of the model, and then apply those coefficients into validation data and calculate the evaluation statistic. And at the end, we average those evaluation statistics to get one value for a given model. So here is some example of root mean square error percent using simple SUR, meaning DBH based SUR, seemingly unrelated regression, and extended seemingly unrelated regression for Douglas fir trees, which is, like I said, a common tree species in Pacific Northwest in the US. And so you can see these are percentages. So we have higher percentage of error in foliage, but because foliage is a smaller amount compared to the bole biomass or the stingwood biomass. So in terms of absolute unit, this will be smaller. So the blue is the extended SUR and the red is the simple SUR. So if we look at the total by using extended, meaning adding height instead of just using DBH as the predictor of biomass, we can reduce some error. And then this is for another species, Western hemlock, another common species in US Pacific Northwest, and we see a similar trend. So here, if the area covered within this polygon is small, then that would be a better method. Ideally, I would have liked this to be inside here as well. So that way I could say the extended SUR is giving smaller error for all the components, but here extended is actually, because this was fit as a system, so overall for the total it is way smaller than the DBH only model, but for some component, especially for foliage, the error was higher than using DBH only model. And this is similar result, but in table and using the generalized linear model, beta and Dirichlet regression. So here we see that, so for Douglas fir, beta is doing good for foliage and bark biomass, not so for the branch biomass, and once again for the bole biomass. And for Western hemlock, Dirichlet is doing better here, not so much here, not so much in other component. So basically, not one model was good for all component, but looking at the properties, beta regression provides 4 different proportion, and those proportion may not add to 1, but Dirichlet provides the estimated proportion for all components simultaneously, and then they would add to 1. So that means it has maybe slightly higher error for some component, but it has that better property of additivity. So in conclusion, root mean square error for total above ground biomass estimates were reduced by up to 9% when DBS and other explanatory variables were included in the model. Methods to predict proportion, they were unbiased and produced smaller root mean square error compared to the SUR. And prediction of proportion in beta regression is independent for each component, which means the predicted proportion may not add to 1, but the Dirichlet regression that solves that problem. So the sum of the proportion will be 1. And briefly about remote sensing approach. Of course, remote sensing has gained a lot of attention in the recent, maybe a decade or more than that. And the application of remote sensing approach in biomass estimation is, first, we apply the models that we just discussed and to the inventory data and get the plot level or stand level biomass. And those values are then regressed using remote sensing metrics. LiDAR is commonly used in the US. For example, terrestrial laser scanning, airborne UAV laser scanning, mobile laser scanning. So there are different types of LiDAR data that we can use. So to summarize biomass estimation, measurement, like I said at the beginning, there is one component which is measurement, which is actually harvesting and weighing the tree, which is destructive. So that means we have to rely on allometric equations developed using sample data. And these models or allometric equations, they are fit using OLS, ordinary least square, SUR, seemingly unrelated regression, or generalized regression approach, generalized linear model approach. And remote sensing is popular, but the accuracy we get from remote sensing models depends on how accurate is the elementary model that we used in initially getting the plot level biomass, and how good is the model to relate that to the remote sensing metrics. Okay, so I think that's all about the biomass estimation, the kind of concept and what we did, what I have done in the past. Next is intro to R and its application.